Hello everyone, our topic for today is all about fluids flow equations. Discharge or flow rate. Discharge or flow rate is the amount of fluid passing through a section per unit of time. This is expressed as a mass flow rate, weight flow rate, and volume flow rate or flow rate. The formulas are given in equation 1, equation 2, and equation 3, where Q equals to discharge in meter cube per seconds or feet cube per seconds. A equals to cross-sectional area of flow in meter squared or feet squared. Epsilon equals to mean velocity of flow in meter per seconds or feet per seconds. Rho equals to mass density in kilogram per meter cube or slugs per feet cube. And gamma equals to weight density in Newton per meter cube or pounds per feet cube. For definition of terms, fluid flow may be steady or unsteady, uniform or non-uniform, continuous, laminar or turbulent, one-dimensional, two-dimensional or three-dimensional, and also rotational or irrotational. Steady flow. Steady flow occurs when the discharge Q passing a given cross-section in constant with time. If the flow Q at the cross-section varies with time, the flow is unsteady. Uniform flow. This occurs if, with the flow for a given length or reach of a stream, the average velocity of flow is the same at every cross-section. This usually occurs when an incompressible fluid flows through a stream with uniform cross-section. In stream where the cross-sections and velocity changes, the flow is said to be non-uniform. Continuous flow. This occurs when, at any time, the discharge Q at every section of the stream is the same. The continuity equation for incompressible fluids are given in equation 4, and for compressible fluids, the formula is given in equation 5 and equation 6. Laminar flow. The flow is said to be laminar when the flow or the path of individual fluid particles do not cross or intersect. The flow is always laminar when the Reynolds number is less than 2100. The flow is said to be turbulent when the path of individual particles are irregular and continuously cross each other. Turbulent flow normally occurs when the Reynolds number exceeds 2 or exceeds in 2100. Laminar flow in circular pipes can be maintained up to values of Reynolds number as high as 50,000. However, in such cases, this type of flow is inherently unstable, and the last disturbance will transform it instantly into turbulent flow. On the other hand, it is practically impossible for turbulent flow in a straight pipe to persist at values of Reynolds number much below 2100 because any turbulence that is set up will be damped out by the viscous friction. One-dimensional flow. This occurs when in an incompressible fluid, the direction and magnitude of the velocity at all points are identical. Two-dimensional flow occurs when the fluid particles move in planes or parallel planes and the streamline patterns are identical in each plane. And the streamlines are imaginary curves drawn through a fluid to indicate the direction of motion in various sections of the flow of the fluid system. Also, stream tubes represent elementary portions of a flowing fluid bounded by a group of streamlines which confine the flow, and the flow nets are drawn to indicate flow patterns in case of two-dimensional flow or even three-dimensional flow. Energy and head. The energy possessed by a flowing fluid consists of the kinetic and the potential energy. Potential energy may in turn be subdivided into energy due to position or elevation above a given datum, and energy due to pressure in the fluid. The amount of energy per pound or newton of fluid is called the head. The formulas for kinetic energy is given below in equation 7 and equation 8. And for circular pipe of diameter d flowing fall, the equation is given in equation 9. The formulas in elevation energy are given in equation 10 and 11, which is the elevation energy equals to the weight of fluid times the elevation head equals to mass times the gravity times the elevation head, and the elevation head is equals to elevation energy divided by the weight of the fluid. For pressure energy, consider a closed tank filled with a fluid which has a small opening at the top. Without pressure at the top, the fluid practically will not flow. The equivalent head for a pressure of P is P divided by the unit weight of the fluid. Hence, the pressure head or pressure energy is equivalent to unit weight of or weight of the fluid times the pressure head, and the pressure head is equals to pressure energy divided by the unit or the weight of the fluid. For total flow energy, the total energy or head in a fluid flow is the sum of the kinetic and the potential energy, and it can be summarized as total energy equals to kinetic energy plus potential energies, and total head E equals to the velocity head plus the pressure head plus the elevation head. Power and efficiency. Power is the rate at which work is done for fluid of unit weight gamma and moving at the rate of Q with a total energy of E. The power in Newton meter per seconds, or watt, is power equals to the discharge times the unit weight times the total head, and efficiency will be equals to output divided by the input times 100%. Bernoulli's energy theorem. The Bernoulli's energy theorem results from the application of principle of conservation of energy. This equation may be summarized as follows. Total head at section 1 plus total head added minus total head lost or extracted equals to total head at section 2. This formula is driven from the given figure above. The Bernoulli's principle in physics, the concept that as the speed of a moving fluid increases, the pressure within the fluid decreases, originally formulated in 1738 by Swiss mathematician and physicist Daniel Bernoulli. It states that the total energy in a steadily flowing fluid system is a constant along the flow path. An increase in the fluid's speed must be therefore be matched by a decrease in its pressure. Energy equation without heat loss. If the fluid experiences without heat loss from section 1 to section 2, then the total energy at section 1 must be equal to the total energy at section 2. Neglecting heat loss in fluid flow, the values that we get are called ideal or theoretical values. From the given figure below, the formula in energy equation without heat loss are shown in equation 19 and equation 20. Energy equation with heat loss. Considering heat loss, the values that we can attain are called actual values. With a reference in the figure below, we will have the energy equation with heat loss given in the equation 21 and equation 22. Energy equation with pump. Pump is used basically to increase heat loss, usually to increase water from a lower to a higher elevation. The input power of the pump is electrical energy and its output power is the flow energy. The formulas that used in energy equation with pump is given in equation 23, 24 and equation 25. Energy equation with turbines or motors. Turbines or motors extract flow energy to do mechanical work, which in turn converted into electrical energy for turbines, and the formulas used are given in equation 26, 27 and 28. And the next subtopic is about energy and hydraulic grade lines. Hydraulic grade lines or HGL. It is also known as pressure gradient or hydraulic grade line. Is the graphical representation of the total energy flow. It is the line that connects the water levels in successive piezometer tubes placed an interval along pipes. Its distance from the datum plane is the value of pressure head plus the elevation head. The characteristics of HGL is HGL slopes downward in the direction of flow, but it may rise or fall due to changes in velocity or pressure. For uniform pipe cross sections, HGL is parallel to AGL. For horizontal pipes with uniform diameter, the drop in pressure heads between any 2 points is also equal to head loss between these points. And for energy grade line or EGL, energy grade line is a graphical representation of the total energy of flow, or the sum of kinetic and potential energies. Its distance from the datum is the values of velocity head plus pressure head plus the elevation head. And the characteristics of EGL is EGL always slope downward in the direction of flow, and it only rise with the presence of a pump. The drop of the EGL between any 2 points is the head loss between those points. EGL is always above the HGL by an amount equal to the velocity head, which is epsilon squared divided by 2 times the gravity. And neglecting head loss, EGL is horizontal. Here are the sample problem. Problem number 18. Water enters a motor through a 600 mm diameter pipe under a pressure of 14 kilopascals. It leaves through a 900 mm diameter exhaust pipe with a pressure of 4 kilopascal. A vertical distance of 2.5 meter separates the centers of the two pipes at the sections where the pressure are measured. If 500 liters of water pass through motor each second, compute the power supplied to the motor. For our solution, the pressure at section 1 is already given, which is 14 kPa, and the pressure at section 2 is 4 kPa. And the discharge is also given, which is 500 liter per second or 0.5 meter cube per seconds. Using energy equation between section 1 and 2, we'll have the equation, which is total head at section 1 minus HE equals to the total head at section 2, which is driven into the pressure or the velocity head at section 1 plus pressure head at section 1 plus the elevation head at section 1 minus HE equals to velocity head at section 2 plus pressure head at section 2 plus the elevation head at section 2. Since the discharge is already given, the velocity head will be replaced by the equation from equation 9, which is used for circular pipes. That's why we have this formula right here. These two formulas are from equation 9. That's why we have this. Then, therefore, by substituting the values given from the problem, we're going to get the value of HE, which is we are going to substitute right there. Since the pipe is using the turbine or motor, we are going to use this equation, and this equation is from equation 28. Then substituting the value of HE and discharge, we will have the value of power, which is required in the problem, and this is the answer. Another problem, problem number 22. A nozzle inclined at an angle of 60 degrees with a horizontal issues a 50 mm diameter water jet at the rate of 10 meter per second. Neglecting a resistance, what is the area of the jet at a highest point of the projectile? Here's the solution. Solving for the velocity of the jet at the summit or at highest point, point A. The Vy will be equals to 0 and the Vx will be equals to Vo sub Ox cosine theta. V sub Ox is the x component of the given velocity, which is Vo equals to 10 meter per seconds. Then Vx or V sub x will be equals to 10 cosine 60 degree and equals to 5 meter per seconds. Then solving for the velocity of the jet at point A, V will be equals to square root of V sub Ox square plus V sub Oy square, which is V sub Ox is equal to 5 and the V sub Oy is equals to 0. Therefore, we'll get the value of V that is 5 meter per seconds. Since we are neglecting the resistance, the flow of the water jet will be continuous. Therefore, the discharge will be Q sub O equals to Q sub A. Then solving for the discharge, we'll get the area of the water jet in its highest point, which is required in the problem. So the answer is this is A sub A equals to 0.003927 meters squared, and this is the area of the water jet in its highest point. And that's all, everyone. Thank you for listening.